What's up? I'm Vin, and today I want to show how to evaluate improper integrals that have infinite limits. So these are the 5 examples that we're going to go through. Here's some notes to help us out, and let's get started. So for this first question here, we have this improper integral, and the best thing we could do to get an idea of what's going on is sketch this thing out. So 1 over t squared plus 9 starts off here at 0 and then 1 over 9. And going in this direction here, the curve just drops down. And it does the same thing in the other direction. This is an even function, so it has symmetry over the y-axis, or in this case, we could say like the function of t-axis. So, we could call this t, and we could say this is, let's say, f of t. So what we're actually trying to find here is the area starting at 0, going out towards infinity. So for these type of questions, the major idea is we want to know, like, does this curve decrease fast enough so that our area is finite? And if it doesn't decrease fast enough, the area diverges. So here, this is what we're actually trying to find. But one of the first things we should do here is rewrite this in terms of a limit. That we're going to fix some point out here and call it b. And what we're going to find instead is the integral from 0 to b. And we're going to do the limit as b goes to positive infinity, because this integral is going from 0 to positive infinity. And we're just going to rewrite, we have 1 over t squared plus 9. So this is what we're going to evaluate instead, and I'll just not forget this dt at the end. And the result of this limit here is going to be our actual area, but if this limit diverges, then we would say that this integral diverges as well. The area is not finite. So what you could do on the side, I highly recommend doing the antiderivative step on the side. And preemptively, I'm going to factor out a 9 from the denominator. And if we take out a 9 from the denominator, we're going to be left with 1 over t squared over 9 plus 1, and then we'll have a dt on the outside like this. And the reason why I want to do this is that it sets us up really nice for a u sub, where I'm going to let u equal t over 3, which will allow us to say that u squared is equal to t squared over 9, which is like essentially what we're going to be replacing this term with. And then du would be equal to 1/3 dt. So then 3 du is equal to dt. So we do a little bit more substituting here, and we're going to have 1/9 times the integral dt is equal to 3 times du. So that's going to go up top in the numerator. And then t squared over 9 is u squared. And then plus 1. And we should recognize this as the integral for tangent inverse. So 3 times 1 over 9 could simplify to 1/3. And now we're going to have 1/3 tangent inverse of u, and then plus a constant. Because this is an indefinite integral that we're doing on the side, we'll make it technically correct by throwing that constant at the end. So we have 1/3 tangent inverse, and u is equal to t over 3. And we have our plus c. But when we do this antiderivative here, because it's a definite integral, we don't have to throw in that plus c. So this is now the limit as b goes to infinity. And we're going to have 1/3 tangent inverse t over 3. And our limits of integration are 0 and b. I prefer to do this on the side because when you have to write this integral multiple times, it gets kind of tedious to keep rewriting this limit notation. So I prefer to do the work on the side. So then here, what we're going to have is the limit as b goes to infinity, and we make the substitution. We're using the fundamental theorem of calculus part 1. So we have 1/3 times tangent inverse. We have b over 3 minus 1/3, and we'll have tangent inverse of 0. And tangent inverse of 0 is just 0, so this is going to cancel out. And just to mention here, depending on where you're learning this, tangent inverse is also interchangeable with arctangent of x. So depending on how you write this, you could write tangent inverse or arctangent. It doesn't matter. Now here, what we have to know to be able to evaluate this limit, I prefer to look at the graph of tangent inverse. And if you look at the graph of tangent inverse, it has 2 horizontal asymptotes. It has a horizontal asymptote at pi over 2, and it has another horizontal asymptote down here at negative pi over 2. And the graph looks like this. So if we want to evaluate this limit here, as b goes to infinity, b over 3, this part goes to positive infinity. But then if you think about it, tangent inverse of positive infinity, you're saying what happens to tangent inverse as x goes to positive infinity? And it's heading towards this horizontal asymptote y equals pi over 2, which tells us that our limit is 1/3 times pi over 2, which we can actually find the area of this region here from 0 to infinity. This area converges to pi over 6. Now for the second question here, we could start the same way by sketching this out. And if we look at a sketch of this starts at 0, 0, this function, and it goes up, and then it starts dropping down where the x-axis is a horizontal asymptote going in this direction. And then the curve starts by dropping here into quadrant 3, and then it picks up here. And once again, the x-axis is still a horizontal asymptote going in the negative direction as well. So what we're trying to find is the area from, we're trying to evaluate the integral from 0 to negative infinity now. So technically I can't call this area because it's signed area. Since it's under the x-axis, it's going to be treated as negative. But what we're looking for here is, does this region here converge to an actual value, or does this curve not go back to the x-axis fast enough, and then this region here diverges off to negative infinity? So when we look here, we could rewrite this first. We could rewrite this as the limit as b goes to negative infinity, and then we're going to replace the lower limit with b. So for this improper integral, we're going to replace the lower limit. And remember what I said before, it does help to do the antiderivative on the side, because then you don't have to keep rewriting that limit notation over and over. So here I would let u equal x squared plus 1. Then du is going to equal 2x dx. And then 1/2 du. Multiply both sides by 1/2, and you're going to have x dx on the right. So that tells us the numerator x dx we could replace with 1/2 du, and the denominator x squared plus 1 we could just replace with u. So then this is 1/2 natural log absolute value u, and then plus c, which is then 1/2 natural log absolute value of x squared plus 1 plus c. And just know x squared plus 1 is always positive, so we could just get rid of the absolute value and turn these to parentheses here. So now we use that to finish this question. We're going to have the limit as b goes to negative infinity, and we've got 1/2 natural log x squared plus 1. We could leave out the plus c because, once again, this is a definite integral, and our limits are going from b to 0. So here we write the limit once more, and we make the substitution. So we've got 1/2 natural log 0 squared plus 1, and then minus 1/2 natural log, and we've got b squared plus 1 when we plug in our lower limit. So we're just using the fundamental theorem of calculus here. Now this piece here, if we notice, is natural log of 1, which is equal to 0. So this first piece cancels out. So all we're looking for here is that we have the limit as b goes to negative infinity, and we've got negative 1/2 natural log of b squared plus 1. But think about what happens here. B squared plus 1 as b goes to negative infinity, you have, in a way, like negative infinity squared is positive infinity, and then positive infinity plus 1 goes to positive infinity. So what happens to natural log of infinity? That goes off to infinity. If we look at a graph of natural log, this curve, it increases very slowly towards the end, but it is just going up forever. So here we have a negative number times positive infinity, which means this limit goes towards negative infinity. So this area diverges. Okay, for this next question here, we'll look at a graph of cosine, but we're just going to look on the positive side of the x-axis, or the theta axis. So if we look here, you can see that the area switches from going above and below. So we have positive then negative area. So if I make a prediction here, I want to say right away that this integral is going to diverge, because if we keep adding and subtracting the same number, we're not going to be heading to a specific value, which is what you need to happen when you're finding limits. So I'm going to predict that this is going to diverge, but if we want to be sure using calculus, we could set up the following expression. We have the limit as b goes to infinity, and we have the integral from 0 to b, and we're looking at cosine theta d theta. So this here, we don't have to do the work on the side. This is a straightforward antiderivative. We have the limit as b goes to infinity, and the antiderivative of cosine theta is sine theta. And we're evaluating this using the fundamental theorem from 0 to b. So then we get this resulting expression here. We have the limit as b goes to infinity of sine b minus sine of 0. Sine of 0 is equal to 0, so this piece cancels out. But if we look at this resulting limit, the limit as b goes to infinity of just sine b, this limit does not exist. So this limit does not exist. And why? Because this function just oscillates between 1 and negative 1. So it's not heading to a specific value as we look towards infinity here. So because of that, what we could say is that this integral from the beginning diverges. So for this next question here, let's look at a sketch of this curve, and we'll call this f of t. And we only care about what's going on the positive side of the t-axis. So we're starting here at 2, and we want to see, does this area converge, the area going from 2 to infinity? Because notice we also have not only a vertical asymptote at t equals 1, we have a vertical asymptote at t equals 0, but the t-axis itself is also an asymptote. It's our horizontal asymptote. So we want to know, does this area converge? Does the curve decrease fast enough to contain this area? So what we're going to do is we're going to just set up our limit. We're going to call this the limit as b goes to infinity, and we're looking at the integral from 2 to b, and we've got 2 over t squared minus t dt. Now this type of integral here, we're going to have to use partial fractions. So we're going to want to set up something like this. We're going to have a over, and just note that factors to t times t minus 1. So we're going to have a over t plus b over t minus 1, and that's going to equal 2 over t times t minus 1. So that's just us, once again, factoring the denominator to t times t minus 1. So to solve for these coefficients a and b, we're going to set up this equation here. We have a times t minus 1 plus b times t, and that should equal 2. Okay, so we're just using the partial fractions method here to evaluate this integral. And one way we could solve for a and b quickly is just plug in test values for t. T equals 1 gives us a times 0, which cancels, plus b times 1, which has to equal 2, which tells us that b is equal to 2. And then if we plug in, let's say t equals 0, what we're going to have is we're going to have a times 0 minus 1 is a times negative 1, plus b times 0 is equal to 2. And b times 0 cancels, giving you negative a equals 2. And if negative a is equal to 2, that tells us that a is equal to negative 2. So when we use this information here, these coefficients are going to help us set up an integral that's going to help us eventually evaluate this limit. So we're going to do that work separately. We're just going to do the antiderivative. So the antiderivative of 2 over t squared minus t dt is equal to, and now once again, we're going to use this section over here. We have b is equal to positive 2. So I'm going to write this piece first, this piece over here. So we're going to have 2 over t minus 1. So we're doing the integral of this fraction. And now a is equal to minus 2. So we'll write minus, and we have 2 over t dt. So we're just replacing this expression here with these two separate fractions because these are actually something that we could take the antiderivative of. And now this is going to give us 2 times natural log absolute value t minus 1 minus 2 natural log absolute value of t, and then we could write plus c at the end because we're writing this as an indefinite integral for now. So what we have is 2 natural log absolute value t minus 1 over t, because when we have logs attached by subtraction, same base, we could connect them by division. And then we have our plus c at the end. So this is going to come in handy for evaluating this integral here in purple with the limit attached, because now this expression here, this particular limit, we're going to write the result underneath over here. So now what we have is we have the limit as b goes to infinity. And we've got our antiderivative we already did. We have 2, and we have natural log. And the absolute value we could get rid of here. Because if you notice, we're going from 2 to infinity. That's where our limits are headed. So if we think about that, if you were to plug in 2 minus 1 over 2 is 1/2. And then if you plug in anything after 2, this is always going to stay positive. So we could just write this as t minus 1 over t with no absolute value. So the limits here have a big effect here on us being able to get rid of the absolute value because we're dealing with only positive values inside of our absolute value here. So now, once again, we did the antiderivative. We still have our limit attached, and we have to complete the fundamental theorem of calculus by plugging in the actual limits. So we're going to have the limit as b goes to infinity, and we have 2, and we've got natural log of b minus 1 over b. See, we're just plugging in b here, and then we're going to plug in 2. We have minus natural log, and 2 minus 1 is equal to 1, and then t is equal to 2. So when we get to this step, now we have enough information to evaluate this. But on the side, just think about this limit separately. The limit as b goes to infinity of b minus 1 over b. Since the leading terms have matching exponents, we just look at their coefficients, and we have 1 divided by 1 is equal to 1. So that's how this limit evaluates. So this is going to be equal to 2 times, and we'll put parentheses. We have 2 times natural log of 1 minus natural log of 1/2. And natural log of 1 is 0, so this cancels. So this is going to be equal to negative 2 natural log of 1/2. But just in case this form is not as simple as we can make it, let's say your professor wants you to go further or your teacher wants you to go further, you could rewrite this a little bit nicer. We could call this negative 2, and then we've got natural log 2 to the negative first power, and you could send this back in as an exponent. So you'll have natural log of 2 to the negative 2 times negative 1 is positive 2, which is going to give us just natural log of 4. So this area from 2 to infinity of this curve is equal to natural log of 4. All right, for this last question here, let's look at a case where both limits are infinite. So we have negative infinity, positive infinity limits. And if we get a sketch of this curve starts at 0, 0. And it starts by, it goes up and then comes back down like this in quadrant 1. And then it does something very similar here in quadrant 3. So in this case, what we want to do is we're going to check both sides here. We have to set up 2 separate integrals and see if both integrals converge. Then we're going to actually have area here for this entire region. But if one of the integrals diverges, that automatically means that this whole integral diverges. So what we want to consider here is we're going to look at the integral from negative infinity to 0 of, and I'm just going to write f of x because I just don't want to keep rewriting this long expression here. And the second integral we're going to look at is the integral from 0 to positive infinity of f of x dx here. So we're going to break this up into 2 separate problems. And once again, we have to see that both of these converge in order to be able to find the actual area. Well, on the side, what we could do that's going to help us for both questions is we could actually find the antiderivative of this integral here. So if we let u equal negative x to the 4th, then du is equal to negative 4x to the 3rd dx, which allows us to write negative 1/4 du equals x to the 3rd dx. So this integral can then be replaced with negative 1/4 du, and then we're going to have e to the u. So that substitution takes care of everything, and that tells us our antiderivative is negative 1/4 e to the u plus c, and then we've got negative 1/4 e to the negative x to the 4th plus c. So that's going to come in handy in a moment when we actually evaluate this antiderivative. So if we look here for this first integral, we could call this the limit as b goes to negative infinity, and we have the integral from b to 0 of f of x dx. And once again, we're just assuming here that f of x is equal to x to the third, and we've got e to the negative x to the fourth. So this limit here is something we have to evaluate to see if the first part of this integral converges. But then what we also have to look at side by side to this is what is the limit as, and let's pick another letter. We already use c over here, so we'll say the limit as, let's say d goes to positive infinity, and we have the integral from 0 to d of f of x dx. So going forward with this, now we go ahead and jump to the antiderivative step. We'll do this integral here in purple. The limit as b goes to negative infinity, and the antiderivative of f of x was negative 1/4 e to the negative x to the fourth power. And our limits are going from b to 0. So if we take care of this first, you'll look here using the fundamental theorem of calculus. We've got negative 1/4, and then we have e to the 0 minus e to the negative b to the fourth. So when this simplifies here, what we have is this is the limit as b goes to negative infinity, and we've got negative 1/4 times 1 minus 1 over e to the b to the fourth power, like this. Okay, so this limit is just something that we have to evaluate. And if we just go ahead and do that now, this actually does converge, because this term here, 1 over e to the b to the fourth power, if you take negative infinity to the fourth power, it's going to go towards positive infinity. And then 1 over e to the infinity goes to 0. So this is going to be negative 1/4, and you're going to have 1 minus 0 on the inside. So plus, and then whatever we get by doing this integral here. So far we have the integral in purple actually converges. And now this one here, we're doing the same thing, the limit, but now as d goes to infinity. And the antiderivative is still negative 1/4, and we've got e to the negative x to the fourth power, like this. But now our limits are 0 and d. All right, now I'm just going to throw parentheses here, because sometimes with this minus sign, it could get a little bit tricky. So just to make sure the notation is nice, we'll throw parentheses around this. And when we go forward with this now, we've got the limit as d goes to infinity, and you've got negative 1/4. We'll just leave that on the outside. You got e to the negative d to the fourth power, and then minus e to the 0. They're like this. So when we simplify this a bit, we got plus the limit as d goes to infinity, and we've got negative 1/4, and then this we could rewrite as 1 over e to the d to the fourth power, and then we got minus 1 here. So this term, once again, 1 over e to the d to the fourth, as d goes to infinity, this fraction is going to go to 0. So we're going to have just negative 1/4. So we got plus negative 1/4 times 0 minus 1. So when we simplify all of this, what we're going to have here is we have negative 1/4 times 1 is negative 1/4, but then we get negative 1/4 times negative 0 changes to plus 0. And then we've got plus negative 1/4 times 0 is going to give us another 0 to add. And then we've got negative 1/4 times negative 1 is positive 1/4. Now here I could have said minus 1/4 times minus 0 is plus or minus 0. So this part really doesn't matter. These terms just cancel out. But negative 1/4 plus 1/4 is equal to 0. So the original integral from negative infinity to positive infinity converges to 0. So you could think of this, since this is an odd function, this area, think of it as equal and opposite, as just canceling itself out. But this actual process here of going through the limits of the integrals confirms for us that this area does converge to 0. Okay, well, this is going to conclude this video on improper integrals with infinite limits. If you found this video to be helpful, please like and subscribe. It helps me grow the channel. And if you got any requests, just let me know what you want me to cover in the comments section below. And thanks for watching.